So hi everyone, I'm Yuan. I'm going to talk about my project started at Hopkins and Genelia about neuron tracking. In this project, we aimed at to track neurons across many days using matrix of the detected units. This method is easy to apply to many datasets, and there is no need to resort datasets during the process. So one important method we used is called Earth Movers Distance, the EMD. EMD is a metric that matches two sets of objects with minimum distances, where the distance can be defined in different ways, and each object has an associated quantity. In this case, we use neurons' physical location relative to the probe and waveform similarity to define distance. As you can see in this diagram, each blue blob represents one neuron from the first dataset. The unique location and waveform indicate the identity of this neuron. And we are matching the blue blobs to the red blobs, which represent the units from the second dataset. And there will be some new units appearing, as in here, and previous units disappearing, as in here, on the second dataset. We assume that there is mostly vertical drift between datasets, and there is location estimation error involved. The formula down here shows how we do the minimization exactly. So to give you an intuition of how EMD works, I want to first start with the simplest simulation using randomly generated units with position uncertainty in each day. We added a 14-micron upward drift between two consecutive datasets, and this is a very typical intraday movement amount. Here we match with only locations or positions for simplicity. We start with the simplest case, where there are 75 units in the region of 900 microns with no unmatched units, meaning that every open circle in this diagram from the first dataset is matched to a closed circle in the second dataset. And this is a normal unit density we see in the real datasets. I'm going to show you trackings on 6 datasets frame by frame in the next few slides. Each frame shows a comparison between 2 consecutive datasets. So we show 4 sections here. The first section shows a one-shunt probe and the positions of all the simulated units on both datasets. The histogram above shows the vertical distance distribution of all the matched units. And the 2 vertical dashed lines here shows a plus and minus 10 micron threshold, in which the match is considered to be a reasonable match. We see that the peak of the histogram is around 14 micron, which is the same as our imposed drift amount. And the spread of the distribution meaning comes from the position uncertainty of the units. The distribution tells us that EMD method can retrieve the homogeneous movement of units. So this section shows the number of correctly matched units in green color and false positives in yellow color, meaning that the unit is matched incorrectly within the threshold. Finally, the survival plot will show the number of neurons tracked across datasets. This is the second day to the third day, and then by the fourth dataset, we started to have some yellow sections here. That in this case, one unit pair is matched incorrectly. And as we go to our last dataset, we see that there's no red sections in this recovery plot because we did not introduce any unmatched units yet. The recovery rate is nearly perfect, and the survival rate decreases here only because the matched units has to be in range to be considered tracked, and they have to be tracked every time. Overall, in this simplest case, we perform relatively well. So how about if we can introduce some more difficulties by making the units denser? Because crowdedness will often cause accidental matches with nearby units. So in this second simulation, we included twice as many units. In this case, we have 150 units in the same area of 900 microns here. still with no unmatched units. Over here, we do have some false positives from the extra crowded units, as you see in the yellow sections here. While the histograms here still pick at the correct distance of 14 microns. So it seems like density is not such a big problem, but in real life, there will be unmatched units, and we can add this to make the simulation more realistic. In the third part of the simulation, we introduced 1/3 of the unmatched units under normal density, which is a realistic estimation of the real data set. The drift estimation is still correct, around 14 micron, even though we have those distractor units. And this can show some of the strength of the EMD method. But the tail of this distribution are much longer, because those unmatched units are forced to match to faraway units since they don't have a real pair. And now we have these red regions over the recovery plot. These are the incorrectly matched units with no real pairs. And this simulation tells us unmatched distractors really make things worse. And when we only use locations, nearby units will be assigned incorrectly, especially with those distractors. So we think having waveform information can hopefully break the tie, and we need to look at real data set to understand, understand it better. So this is the real data set. The layout of this data set, is much like the simulation, where we imposed a 12 micron upward drift on the second data set indicated by the closed circles here. Note that we only have around half of the units with known pairs. So considering some of the units also potentially have a real pair, but just we cannot know for sure, there is roughly 1/3 of these distractors without the true match, even in the real situation. So if we look at the histograms, the peak of this distribution lies on the 16 micron, as indicated by the light blue line, dashed line over here. And this is a combination of the 12 micron imposed drift and 4 micron measured drift in the original data set. So far, all the examples above show how EMD can detect homogeneous motions of units and is robust for estimation errors. Then I'm going to briefly go over the main steps of the method. In this method, we use unit sorting as the input. We estimate the between session drift from the mode of the EMD distances of all matched units, which hopefully accounts for the rigid drift. Then the local unit assignment in the drift-corrected units account for the non-rigid drift. Finally, we apply a z-distance threshold to remove false positives, because EMD is an optimization method that assigns a match for every unit, regardless of whether it's biologically plausible or not. To test the performance of our method, we use the same data set from the Steinmetz 2021 paper, which Anna just talked about. The visual fingerprints are used to establish correct matches between data sets. To reduce uncertainty in curation, we included all the units labeled as good by kilosort and conducted no post-processing steps in unit selection. And this diagram, this Venn diagram shows you that the kilosort good units are roughly a half of all the sorted units we have. And the units with reference information is around 29% of all the kilosort good units, which means it's around like 15% of all the sorted units. So overall, we achieved a 99% accuracy for dataset 1 week apart and 95% accuracy for datasets 5 to 7 weeks apart, and after applying the threshold on the reference units. This result is comparable to the Steinmetz 2021 paper, while our method for calling accuracy is somewhat different from theirs. The purple bars here in this diagram shows units without the reference information, but is qualitatively similar to the correctly matched units. So we think we can retrieve these units. So, so all the previous results I have showed you so far considers the reference units, but we want to ask the question, are the reference units really representative of the entire population of the kilos or good units? So unfortunately, the answer is no. We looked at the distributions of the reference units and all the kilos or good units and find that the slopes and tails are both different. So I previously mentioned that EMD make matches for every unit in the set, but in reality, some of them do not have a real match, as we mentioned in the third simulation, and that is where the false positives come from. However, that's not the case in the reference units, because the definition of reference units already makes sure that they have to appear in both datasets. This Venn diagram aims to help you understand that the relation of all the kilos or good units and the units with real pairs. Since we normally do not have reference information in our datasets, we have to consider all the kilos or good units. We find that we can best fit the reference distribution as a folded Gaussian distribution and the rest of the units as an exponential distribution. So all the kilos or good units is a combination of the two distributions. Then by fitting the slope of the exponential distribution and the fraction of unmatched units, we can estimate the false positive rate with different thresholds by integration. And that is about 27% at 10 micron. So finally, I want to show you the units that we tracked across all the datasets up to 7 weeks apart. We looked at consecutive datasets and followed 106 units over 3 animals. The survival plot here shows you neurons from 3 animals with different amounts of reference information and gives you a sense of how many units we can track over 7 weeks. We also checked their locations, waveforms, and firing rate to make sure they are indeed the same neurons. So in summary, EMD can detect drift, enables tracking of units given location and waveforms using output from individually sorted datasets, and gives an accuracy similar to concatenation method for a receptive field validated reference units. Second, reference units are a special set of all the units. Because real dataset has unmatched units, the false positive rate can be up to 27%. Lastly, we learned that a method to remove difficult to detect units will reduce the false positive rates and improve the overall tracking reliability. Since in this method we used published data, we don't think we have enough data to fully validate our method. So we want to concentrate in this talk is how EMD works well in detecting drift, but it will be very helpful if you can add an additional step in screening the data set first. For example, by adding some quality metrics to eliminate some of the units, so you can have mostly reliable units in the matching, and the false positives will be much lower. Okay, thank you.